Okay, so let us start the last talk of this day, and our speaker is Mauricio Díaz from Universidad del Bío-Bío, and he will talk about levels of local distributional chaos for Turing machines. So you can start.
Thank you very much. Thank you for the possibility to talk. Now I'm going to talk about level of local chaos for Turing machine with moving tape in sense of, in two senses, technically. That is the sense of Lee-York and distributional chaos. I hope you enjoyed. Thank you. Well, the idea of this work bore about three questions.
Sorry, Mauricio, could you speak a bit louder?
Oh, yes, I'm sorry. Well, the motivational question, or all the motivational questions, provide from three questions that I did during this work. And well, first of all, if one machine can generate other level of its symbolic dynamics, in other words, if you can describe one machine in terms of other type of systems who has the classical behaviors. Secondly, the dynamics of TMT with chaotic behavior can be studied in one orbit generated by other level of chaoticity, not just the more classical the level of chaoticity associated with antecedable level. And the last question is if the machine that I will study can be generated by our local rule being by the antecedable levels. Well, in general, I will describe level of chaoticity in terms of dynamical system, and I define one type of Turing machine in terms of dynamical topology. Well, to start with this idea, I start defining the chaos in sense of Lee-York, in which I have here a topological dynamical system with a metric and a self-continuous map in X, and I define a pair point in the Cartesian product, like is Lee-York pair if it's proximal but non-asymptotic in other terms, or the sublimit, the inferior limit of the distance between the orbit is 0 by one part, and the second part it is the sublimit between the distance between the point of the orbit is greater than 0. If we have a set who contain at least two elements or a scrambled set, we say that this system is chaotic in sense of Lee-York if X contains a countable scrambled set. Some other definitions about it include the Lee-York sensitive, in which there exists a parameter such that for any point and any other parameter, there exists a limit point in X with the distance bounded by any parameter, such that this point has the same property, but with the difference with respect to the other, that the sublimit of the distance is less of this parameter that we define. Other definitions are densely chaotic, in which the pair is dense in the product space. Generally chaotic, in which is residual in the space, and topological chaotic when the topological entropy is positive in the sense of Bowden and Dinaburg definition. Other definition who was proposed in 1994 is a distributional chaos, in which instead to study the relations of a proximal behavior, this basically is similar, but using a probability measure in this case instead to use other type of things. So if we have a pair of points in the Cartesian product and we define an integer greater than 1, we define here an increasing element, an increasing sequence in the natural. Well, that definition is not the classical definition of distributional chaos. It's more associated with with a variation proposed in 2007 for associate this same behavior for an increasing sequence. And we can find here the sequence of distance and a distributional function who goes from the Cartesian product time the parameter time the action of the dynamics, and it projects a unit interval, and we can define it like a time average 1/n time the sum of all the elements who Gauss count whose characteristics who represent instant in which the distance between those elements is bounded by belongs to this interval. So next we define the upper density and the lower density as the upper density as the sublimit of this distributional function with respect to, and the lower density the inferior limit with respect to t. After that, we can say that a pair xy in the Cartesian product for any distinct pair in an uncountable scrambled set is called distributionally chaotic with respect to this sequence. I denote it like DCS. If for every parameter t greater 0, the upper density defined by any parameter is equivalent to 1, and if there exists some element greater 0, such that the lower density is equal to 0. In particular, when the sequence is the whole element of natural, then the system is distributional chaotic of type 1. Also, there exist other type of definitions proposed later, in which there exists some parameter in which the upper density is strictly greater than the lower density, including with the upper density equivalent to 1. We can refer it like distributional chaotic of type 2. And if we just include this definition, we are talking about distributional chaotic of type 3. Naturally, the distributional chaotic of type 1 is a stronger form, and that implies distributional chaotic of type 2, and that implies distributional chaotic of type 3. Also, the distributional chaotic of type 1 imply Lie-Jork, and imply the distributional chaotic with respect to increasing sequence. Well, other part who was proposed later are associated with the level of distributional chaotic, in which we define a strong level of distributional chaos. Well, they define a strong level of distributional chaos, in which for some parameter between 0 and 1, and any distinct points in S, the upper density is equal to 1 for any parameter greater 0, and the lower density, the epsilon, is less or equal B, and B is strictly less of 1 for X and for some parameter. The same one can say about the strong DC3, in which they restrict the parameters A greater than B and greater or equal 0, in which these properties are true. Naturally, bound property imply the other classical property, but not conversely. Well, so some property that we can see during the bibliography are the following. In this case, in which if we start working with certain dynamics with certain property, like with mixing, for example, we can find by the result of other authors that the weak mixing imply Lie-Jork sensitive, and that's implied sensitive, and that's it can imply Lie-Jork chaos from some form and that one can go to this part. Other form to study is, well, defining the weak mixing who are associated with the transitive property, in which this element and the sensitive are related with some level of chaoticity that I will talk later. Well, but these ideas now we will study in relation with other level of chaoticity defined by the collection of the action. In this case, we define a family associated with the set of positive integers, and P the collection of all the subset of N. So this collection or family is called Furstenberg family, and that means that it's a hereditary of words. In other words, if F1 belongs to F2 and F1 belongs to F, to the family, then F2 belongs to the family. Naturally, the whole set of positive integer belongs to the family. There are now some results associated with the work of Furstenberg in 1981 and in Huang in 2012 about some properties that are really interesting by this presentation, but especially this set in which we denote as the collection of all infinite subsets of natural. Well, especially today, our principal results are associated with some part of the Furstenberg family, which we note like block family. So if we define here family, the block family is denoted like BF, and it's right as all the subsets of the natural, such that there exists an element of the family, and for any element of n, there is another element of natural, such that the sum between this element at any intersection of the element of family is contained in A. Some properties here under this form you can find here, in which the block of the block family is equal to the block family, and the block of the collection of all infinite subsets of the natural is the same. Well, our objective now is to find results associated with the part in which you can see in green. So the linear chaos, the distributional category respect sequence, the sensitive, the BF sensitive, and those parts. By now, well, by studying it, we will use the one-side full shift system, and I showed some interesting equivalence associated with the structure of this form created by the sequence of the block family. In this case, I draw the neighborhood as a tree form in which include the two symbols 0 and 1. Okay. Next, well, about the one definition before to find the results, we define a pair as a dynamical system with topological metric. Then the system is F sensitive if there exists some set of the natural, some element of the natural, such that for any set inside of the natural, the time set who is defined by this element, and this set is all the natural, such that this element x e generated by e is equal y generated by e, and the instance in which we iterate by the shift function, the restricted by m, are distinct, and this element belongs to F. We can find the same definition by block family, but just finding that the time set belongs to the block of the family, the BF. Well, now one proposition about the construction of the idea is to describe an increasing sequence, a node like BI, and a set, an arbitrary E inside of N. So with the, well, this increasing sequence is inside of the time set with the difference between BI plus 1 minus BI for any I is bounded by M, strictly sense, and NME belongs to the block family. Using that, the idea of the proof basically is abstract, is technically defining an increasing sequence AI inside of natural and an element of the family such that AI plus this element belongs to A. By it, we define a pairwise disjoint sequence with capital A inside of A with those properties. The first one is true since the integer, the positive integer is the maximum element who is contained in the family. And this element is the last way in which we can construct pairwise disjoint sequence. It's easy to check that the capital AI is inside of AI plus 1, and also that this part is inside of this interval, this natural interval, since F is a family. Using that, we need to be careful with this result when the supremum of this element is equal infinite, because we can have some problems about the result of this problem. For this reason, we restrict this idea to some m. So it's easy to check by defining an element pi in one set that we define that ai, where li is inside of ai as a proper sense, and we can define by a fixing I in the natural, an element of natural, the intersection who is the finite union of this Lj with the length, with the sum of the length less or equal I. With it, for the develop more the construction, we define one lemma in which we suggest that if we define an element of the increasing sequence, this element being less strict set of m for some m, any set of words, there exists at least two elements of a sequence or nowhere in some word. With that, we can construct an idea about how to describe the uncountable set. After it, we construct the idea about those elements in which this circle implies that all those elements is the length of all these elements that we construct in terms of the sequence that we are working. After that, we define m as a positive integer and also define a sequence with this form, in which b1 is equal 1, bam is equal plus 1 is equal bam plus m, and well, bi plus 1 is equal bi plus I in modulus m. And this sequence is by a in natural. So next, we fix an ai in natural, and we know that ai plus 1 is equal this form. So ai plus 1 is generalized, it is equal to ai plus a squared plus I minus 2 over 2. So we can construct a natural interval with this form, in which we have I squared plus I minus 2 over 2 until I squared plus 3I minus 2 over 2, with A1 plus N0 belongs to the block. Okay, in particular, we can take many elements, for example, for m equals 4, and we can construct from it some form who involves to this structure, in which in one instant we can find elements in which, if we compare two elements, the elements in one part are equal and another part are different, but that repeating in infinitely many times using using this sequence. And with that, we can propose the following part, in which, being this dynamical system with this form, the system has linear chaos and has distributional chaos with respect to some increasing and proper sequence. However, evaluating one of the elements of this sequence, we prove that the system is not necessarily distributionally chaotic of type 1. Well, the idea of find the system who is distributionally chaotic with respect to increased sequence, we can find that for any k natural, this element bik is different to ik for some element. Other proposition that we have by this structure is that the system could be distributional chaotic 2, but not distributional chaotic 1. But we need to review this part of the proposition 6. Well, about the second part, we define now the Turing machine, about its generalization. Well, I introduced it defining the Turing machine as an abstract mathematical computational model consisting of a tape of infinite length divided into cells with given input and head who read the input tape, which was introduced in 1936. the tape is this part in red and the head is part in yellow, who has two directions, and in terms of the infinite sequence of the left and the right, in which X is the set of the configuration of samples, and S the set of finite states. And we define in this machine a map who goes from the product between the finite state times the set of symbols to the same, but with the directions. In the following work, we don't use the blank symbol. In other words, we just use the machine about the instruction has two options: moving to the right or the left, represented by -1 or 1. About that relation with the dynamical system, the Turing machine was introduced by Moore in 1991 in this work about generalized shift, and formalized by Kurka in 1997, in which he defined the type of Turing machines that are relevant about the property of compactness. One of them, and that's the idea that we expressed today, is the Turing machine with respect to the tape without moving the head. So in this case, what means that? Well, we define a Turing machine with moving tape or TMT as a system who is inside of this product, and instruction who apply them by moving the tape instead the head. We can define this property. Well, some examples about it is, well, this map with that instruction in which the state doesn't move from the process, and just change the element by finite configurations. So in this case, we have 6 elements, for example, in a machine with 3 elements. So by this case, it's we can find a reversible function in which who has inverse and has other properties that was studied above. Well, some example of Turing machines in the sense of topological dynamical system was proposed by Rodrigo Torres and Pablo Concha in 2016 and 2020, and are the SMART and BinSmart, who are machines with 4 states, and that with a state, and with 3 symbols, 0, 1, and 2, and this with 2 symbols. They prove that those machines are aperiodic, symmetric, and minimal, then transitive. Okay, now following with the idea, our question is how the relation between these machines with the sensitive conditions. That is the other idea that we want to study. And well, first of all, we define a sensitive map when there is a finite observation window, denoted by double B, inside of SID, such that for any element who can be finite or infinite subset of SID, there and for any point in the space, there exists an element of X and an element of natural, such that, well, it works the same that the previous definition about the shift, but with this map. And I will reference to it like classical sensitive with respect to the machine. Well, about the Cantor metric, about the metric space, naturally, we can define it like a compact, and the metric can be defined like this form, in which we have that is 0 when all the elements of the left side and the right side and the state are equal, and 2 power minus a when we have the complement and otherwise. So we can, next we can define that delta is a continuous map, and we can rewrite it like the product, like between all those elements who belongs to the continuous maps also. After it, we propose the following result, in which the system is delta sensitive if and only if each map of this product is also sensitive, which is not so complicated to prove. After that, we define the same idea, but with respect the families. So we defined the system who is F sensitive, well, basically about the same, but in which the element of natural with the same conditions belongs to the family. About that, next we introduce a new rule for studying the dynamic of these machines. Well, here we have a configuration with the form AI plus 1 until AJ, with the state SLI. After one process, it goes to AI plus 1, AI plus 2, AI plus J, AJ, and SLI plus 1. Well, technically that is an infinite configuration, but this is, well, that's a form to say that the element technically is adopting the shift properties. And this Turing machine, we can call like rule 1 to satisfy this idea, and the instructions are denoted by the Turing machine with respect to the tape. Well, naturally, some ideas about it is the sequence is increasing over the natural, and secondly, it's the process which has a dynamic generated by a suborbit, which it preserves the property of our intensity. Our intention is study forward orbits. Well, some examples about this type of machine with rule 1 are the machine with just one direction, well, the full shift, the machine with periodic point, or the mortal machines, in which you can find the non-reversible machines. So for this reason, that is a particular case, but we will study two different cases. Well, about the first case, in which they have rule 1, we can suppose that the Turing machine is equal between them, and the first term, well, technically the same that working about type of sensitive. So using that, we can propose the following result, in which if we have the product of the system, which while having rule 1, there is a subsequence Li, such that there exists at least one element of the finite sequence, which is into the time set. And this idea can be studied proposing with the next proposition about the corollary 10, in which if we find a product of cylinders and we have X line over line A0 until AJ plus minus 1, we can construct a finite set with this form inside of the time set. If I extend this result, we can define a machine with the same input with outputs, as you can see that there. So with Q, with all those Q as an arbitrary elements. And with that, we can construct a set with the form NR equal J plus the sum of R prime equal 1 to R of KR prime and J otherwise. Using that and assuming that J is quite big, we can propose the following part, in which if the system has rule 1, then this sequence can form and is inside of the heading time of double B and comma E, being double B an element who is inside of the integer. Other proposition right here is that the system with rule 1 is block infinite, but technically is infinite. And also, if this idea it has rule 1, in addition, there is an R prime greater than 1, such that KR prime is greater than 1, and the system is chaotic, hence in sense of Lee-Jork. Well, now the other machines that has no rule 1 are the machines who has properties like being aperiodic, for example. So the previous machines that I mentioned, for example, the Smart and BinSmart are an example of it. And with it, it's really more easy to propose and prove that the smart is chaotic in sense of Lijorg, since the smart is mixing about the result of Rodrigo Torres, and the BinSmart, the one proposed about the BinSmart is chaotic in sense of Lijorg, so since it has the same relation with the smart. After that, we can find that these machines, starting from the sense that has mixed that minimal properties, we can see that the system has positive behavior, and since it is with mixing, we can relate it with sensitive, and we can construct other definition of chaoticity that is interesting to study in some particular cases in dynamical topology, like Robinson chaos, in which you have just a system with each transitive and has sensitive independent of initial condition. So since we have here the transitive by the results of Lee, this element has technically related technically with the collection of infinite subsets. So basically, the definitions of block family in terms of the Robinson chaos are equivalent with the definition of F chaotic, since the family is in a collection of infinite subsets. With it, we have the particular non-rule system that are known as F Robinson chaos and BF sensitive. Now, basically with it, the results that we obtain with that are that if we have a TMT configuration independent of the rule 1 or not rule 1, it has Lijorg chaotic, and it has distributional chaos with respect to increase in sequence generated by the block family. And secondly, as we construct system who contain minimality, the system has F Robinson chaotic and is weak mixing. Well, finally, my open question is to find a machine who are, because we are not just the Turing machine with moving tape. We can construct other type of machines. So not by all the machines, it's not necessarily true that all the machines has not distributional chaotic of type 1. So one can construct an idea about it. Secondly, find a TMT which has F scrambled pair. About this one, we have yet to study this relation, who was proposed in 2007, and it was really interesting at the time to describe this type of system, but using the Michalski theorem. Finally, the Turing machine in sense of dynamical system has ergodic measure, but that is still an open question, since there is not many results associated with this type of machines in this sense, this topic. Finally, the books that I read are about the works of Rodrigo Torres and Aníbal Guajardo, other works of chaoticity about Motatu, the works of Oprotka about the entropy of Turing machine, and other works about the level sensitive, like Lijorg sensitive. Well, that's all. Thank you very much for your attention.
Okay, are there any questions? Okay, let us thank our speaker again. And this is the end of talks for today, and we will resume tomorrow morning.